So to continue, we can talk about web deployment. And to get started here, I want to talk about terminology. Just there's different terms used that I wanted to make sure we're all on the same page about. So sometimes the word inference is used, and that refers to making predictions, so not training. So there's training time, inference time, prediction time, production. All these things refer to making predictions. So model serving is something that you hear, and that refers to like a machine learning specific deployment method. And it's usually focused on optimizing the use of the GPU in your model. So web deployment, I want to cover REST API. So that means serving predictions of your model in response to HTTP requests. I say canonically formatted because that's what REST means. There's just kind of a set of verbs like get, put, post, whatever. And you can serve predictions in response to those. The web server that's running, we call that the prediction system. So our options for doing this, we can deploy our code to virtual machines, virtual machines, scale by adding instances. We can deploy our code as Docker containers. We can scale that via orchestration. We can deploy our code as a serverless function, or we can deploy our code via a special model serving solution. Those are the 4 options I see for a web deployment. This covers, the prediction system, the serving system parts of our project. And I think the relevant tests here are canarying models before serving, being able to roll them back, and probably that might be it. So the first thing you might think to do, this is the old school way, is like deploy code to your own servers. And we don't even talk about that because we don't do that. But what you might want to do is deploy your code to cloud instances. And maybe I should talk about why we don't really deploy to our own servers. And the reason is really scale, right? Like you won't be able to buy enough machines fast enough if your application or the usage of your model really goes up. And if the usage of your model might be cyclical, so maybe it really spikes at some point in the day and then it drops back down. Might be expected, might be unexpected. But if you own all the servers that you have to run on, then you're stuck with like a huge fixed cost, no matter whether they're actually serving predictions or not. What makes more sense is to use cloud instances for web deployment. So here, like the old school way to do it is you basically get an instance, you provision it with all the stuff you need. So you install Python, you install your app code, all the requirements. And then the instance runs, it serves predictions. If you need more predictions, like more requests for predictions are coming in, you can increase the number of instances. And you can do that via auto-scaling. So essentially, like, as requests come in, they hit a load balancer. If the load balancer sees that all the machines are already busy, it can start another one, and so on. And this is the old school way to do things. So the cons of this old school way is that provisioning can be very brittle. So like you have to install the OS, install the version of Python, install all the binaries and libraries you might rely on, the Python requirements. And then because you're auto-scaling, that might help because you'll shrink back down. But there'll still be times where you're paying for instances even while you're not using them. It's kind of like as it shrinks and grows, there's going to be times where they just kind of sit there. The better thing to do in 2019 is to deploy Docker containers and not provision your own instances. So here you package up your prediction system as a Docker container, and then you are able to deploy your Docker container onto some kind of cloud infrastructure. That could be Kubernetes, that could be AWS Fargate. But the crucial thing is that Docker is the intermediate kind of artifact. The cons to that is that even though it's now a nicer experience because it's not as brittle, you still have to auto-scale the servers. You're still paying for the uptime of the underlying servers and not just the execution time of your container. What we'd like to have is to be able to just say, like, here's my container, and then please, Amazon, figure out how to make enough of them in response to all the requests that are coming in for them, and then shrink them down immediately if no requests are coming in. And I don't care how many machines you use. I don't care about basically anything. I just want to provide you the container, tell you that each container needs 2 CPUs and 6 gigs RAM, and then have you figure out the rest. So the closest thing to that we have today that is an option in the big cloud providers is serverless functions. So this, the word serverless is something you might have heard. Basically, it means that your application code and whatever dependencies you need are packaged up into an artifact that's not a Docker container. It's usually a zip file, could be something else. And then there's kind of an entry point function as part of that. So Amazon Web Services Lambda manages everything else for you, so they can scale that package up to 10,000 concurrent requests per second or more, load balance it for you, monitor it for you, and also only charge you for the time that it's actually being executed. And I put in a little meme that says, your servers can't go down if you don't have any servers. So the cons to that is that it's really quite a stringent deployment requirement. So you have to fit in your whole thing in less than 500 megabytes of code and binaries, less than, I believe, 5 minutes, might be different now, maybe 30 minutes execution, less than 3 gigabytes memory, at least on Amazon Lambda. I'm not sure how it is on Google Cloud. And you're limited to only CPU execution. So whereas even with Docker, you were able to provision a GPU and use a GPU, here you're limited to a CPU. It's pretty easy to canary. It's pretty easy to roll back. So all the DevOps stuff is made super easy for you in the serverless world. Model serving is web deployment specifically for machine learning models, potentially specifically for deep learning models. Tensorflow Serving is a canonical example. There's the model server for MXNet, which is the Amazon kind of framework of choice. There's open source projects like Clipper. And there's whole kind of software as a service solutions like Algorithmia. And some of the all-in-one solutions we saw yesterday, some of them also have model serving part to them. And the most important feature these serving solutions provide is really batching requests for GPU inference. So these are useful when your inference has to use GPU. Oftentimes, for a lot of things that people do, you actually don't need the GPU for inference. You need the GPU for training because you have to do the forward pass and then the more expensive backward pass, and you have to do it thousands of times. But at inference time, you don't have to do the backward pass. The forward pass might actually not be that hard to compute, and a lot of time you just need to respond in let's say half a second, which is plenty of time even for a CPU to process the input. But if you do need a GPU, for example, your model is too large it just has to do so much computation that you just need the GPU. Well, there it gets important to actually batch requests that are coming in onto the GPU. Because otherwise, when a request comes in, you say, OK, it's a mini batch of size 1. I run that through the GPU. And then while you're running it through the GPU, another request comes in of size 1. You have to send that through the GPU. It's better to have some kind of almost a queue system here. So as requests come in, you put them in batches. And then maybe every second, you run the batch through the GPU. So that can be that's what model serving allows you to do. TensorFlow Serving, basically able to serve TensorFlow predictions at high throughput like this. If you use Google Cloud Platform all-in-one solutions, there's going to be deployment options that use it. And if your TensorFlow model is like a nice TensorFlow model, then it will work with this. It might be overkill unless you know that you need to use the GPU for inference, or unless you can explain why you need TensorFlow Serving. I would start from the position that you don't need it, and then try to understand why you do need it, as opposed to what the TensorFlow documentation makes you believe, which is that you definitely need it, right? And then you're kind of off on your own if you don't use it. So like I said, MXNet is a competitor to TensorFlow and PyTorch and other things like that from Amazon. So SageMaker uses that. Clipper is an open source project here at Berkeley. It has nice to haves like state-of-the-art bandit and ensemble methods to intelligently select and combine predictions. So that might be interesting things like maybe you run an input, you run inference in multiple models, and then you have something on top of that to combine them. So if you know you need it, then it's there. I would assume that you don't need it at first. Algorithmia is software as a service. It's one of the examples of startups and all-in-one solutions that promise very effortless model serving. I personally don't have experience with it. It seems like it could be a really nice experience, but it could be something that doesn't make sense for your company because you already have a DevOps process that they don't want to relinquish and have the machine learning team use something totally different. There's a startup called Seldon, which is focused on deployment. It runs on top of Kubernetes, and specifically it integrates with Kubeflow, which is this whole kind of machine learning framework for Kubernetes. So it gives you that kind of cool stuff too, bandits, outlier detection. And it gives you a UI to kind of visualize your deployed models, maybe audit how the things are happening. Unfortunately, I couldn't find a screenshot of any of this stuff. So if you use it, please post some screenshots in Slack. My takeaway is that if you're doing CPU inference, which is what I would try to do, unless you really establish that you need GPU for inference, you can get away by either deploying to Kubernetes and kind of like auto-scaling that, or going serverless. And the dream is that it's as easy to deploy Docker containers as it is to deploy Amazon Lambda. I don't think we're there yet. But the next best thing is either serverless, like Lambda, or Docker on some kind of orchestration framework. Now, if you're using GPU inference, then things like TensorFlow Serving make sense. You guys have questions about that?
There's a question around really large models for inference. So if you have a model that is so big that maybe it can't even fit in GPU memory,
oh, yeah.
Are there any solutions for serving a model like that?
Well, if you have a model that can fit in GPU memory, presumably because you trained it with model parallelism, so you broke it up onto multiple GPUs in training, what do you do at inference? That's a good question. I would try to not be in that problem space. And there's going to be some things later on in this lecture that can ameliorate some of that, like model distillation. I think your choices are just either using multiple GPUs or just provisioning a CPU instance with a large amount of RAM. And then it'll be slow to compute, but at least it'll fit in memory of that instance.
There's a question around saving the weights of your model, and specifically around pickling them or using joblib, or is there a better way? And what do you recommend there? And why not just pickle or joblib?
I would work with what the framework encourages you to do. So try to save the TensorFlow model using the TensorFlow.model.save, or whatever the function is there, keras.save model. If you're using PyTorch, save it with PyTorch.save, and not try to do anything else. This might be a question about like an sklearn model or something. I mean, as much as possible, I would use the framework save code, because that's going to be the tested path. Otherwise, you're going to have your own path, which you'll probably have to write tests for.
There's a question around intellectual property and serving. So can you comment on, if you need to be careful about the intellectual property of your code, is that something you need to be thinking about when you do deployment? And are there any implications of how you choose to do deployment on that?
Well, the question might be, when you're using software as a service for deploying your model, can you rest assured that it's not going to get stolen? I think the answer should be, you got to read the terms of service, and presumably there's a service agreement, right? And any sane one will say that they don't have rights to use your model for anything. So yeah, it's worth reading this terms of service. But if it says that they have the right to use your model for other stuff, then don't work with them. If the question is, can a deployed model's source code or trained weights be somehow obtained by sending requests to the model, then that's a good question. And that kind of gets at security of machine learning models. and I don't have much to say about it, but there's a attendee in the audience, Abraham over there, who might have things to say about it, and maybe we'll post it in Slack. But that's an interesting question, is like, how much can you learn about a deployed model simply by sending requests to it and seeing what it comes back with?
There's a couple of questions around CPU versus GPU inference. Is one of those more common than the other? And then why, like, what would the decision process that you would follow be to use GPU inference instead of CPU inference, like if you're going to do that?
Well, I would try to not use GPU inference because GPUs are expensive, period. I would only use GPU inference if the model that I had to run inference on was slow to run on the CPU, or maybe the volume of requests coming in was such that it just made sense to kind of batch up requests and send them through the GPU together. So if I have to answer 30 requests, or I don't know, 100 requests every second, and it takes me takes me like 200 milliseconds to run each one on the CPU, but it only takes me like 2 milliseconds on the GPU, then yeah, let's batch them up, run them all, and then be able to do that. But it will be more expensive. And most things don't have to answer, usually things are spiky in the world, right? It's not often that you have like a sustained heavy workload in your inference deployed model.